Hello everyone, welcome. This is a presentation of the paper Predicting and Using Target Length in Neural Machine Translation. My name is Zijian Yang. I'm a master student in RWTH Aachen University. I'm going to introduce this topic in following parts. First, I will give a short introduction to this topic. Second, I'm going to show how we build up the model to predict the target length. Third, I will introduce the training criterions. Fourth, I'm going to explain how to utilize the length prediction in decoding steps. And at last, some experimental results. Okay, let's start with a short introduction. In recent years, neural network models have achieved great improvements in machine translation tasks. Among kinds of different architectures, transformer model delivers state-of-the-art performance. However, despite the success achieved in neural machine translation, current NMT systems do not model the length of the output explicitly. In this case, length normalization is needed in beam search, since without length normalization, regular beam search prefers shorter hypotheses. The simplest way of doing this is to normalize the score of the hypothesis by its length. Although length normalization appears to be simple and effective, it is still an additional technique to help a machine translation model that cannot handle the hypothesis length properly. Thus, in this work, it is proposed to model the target length using the neural network itself. Our model is based on transformer architecture, and the target length is modeled by a subnetwork. During training, the length prediction task and the translation task are jointly trained. As for the usage of the length prediction, it can influence the whole network implicitly, and the predicted length can be applied as an alternative to length normalization in beam search. Okay, here's how we model this length prediction task. We build up a subnetwork to predict the target length, which only needs the information from source side. The input of the subnetwork is the transformer encoder output, and the length prediction task is considered as a classification task for different lengths in the range of 0 to 200. To get the input of the classifier, we compress the whole source sentence to a single vector. Besides, to inject the source length information explicitly, we map the source length to a vector by a length embedding matrix. Okay. Then let me introduce some more details about the subnetwork. Firstly, we concatenate the encoder outputs and the word embeddings together and map them to new vectors z. Then we set the length of z fixed to 200 by clipping or zero padding. Namely, capital J is fixed to 200. Then we utilize convolutional layer, max pooling layer, and the linear projection to compress J dimension. Then the vector is concatenated with the length embedding. Again, this concatenated vector is projected through a linear layer onto a vector with 201 dimensions. At last, the length probability distribution is obtained by softmax. The predicted target length is the length with the highest probability. So the length prediction model can be used in three ways. The first one is to influence the whole model by multitask learning, since gradients of the length model will propagate to the translation model. In this case, there is no other connection between the length model and the translation model, so we call this no connection. The second one is to pass the length information to the decoder side, which is called cross-concat. We concatenate the length prediction vector to the outputs of each decoder layer and map the new vector to the original dimension. We hope the decoder could learn about length information implicitly. And the third one is to employ the predicted length as an alternative of length normalization in beam search. We will introduce more details in decoding part. Okay, now let me introduce how to train the model. During training, KL divergence is used as the loss of the length prediction task. QL is the probability from model outputs. PL is the target distribution given by a Gaussian function added with a neighborhood reward D, and then normalized. In this distribution, there's only one true label with a high probability. In contrast to cross entropy with label smoothing, in which other labels are treated equally, due to the Gaussian function and the neighborhood reward, the probability PL becomes smaller if L is further away from L target, which creates the desired relationship between each class in the classifier. For the translation task, the loss is cross entropy with label smoothing, and the final training loss is a weighted sum of translation loss and the length prediction loss. Okay, and now here's the decoding part. As introduced above, length prediction can be employed as an alternative of length normalization. In this part, I'm going to introduce how to use length prediction to guide decoding steps directly. Since the predicted target length cannot be 100 accurate and the source sentence can have multiple possible translations of different lengths, we control the length of the inference by penalizing the score of the end of sentence token during beam search, rather than forcing the length of the inference to match the predicted length. More specifically, if the length of the hypothesis is shorter than the predicted length, the EOS token score is penalized. If the hypothesis is longer than the predicted length, the EOS token score is rewarded to facilitate the selection of the EOS token in beam search to finalize the hypothesis. We choose the logarithmic linear function as the penalty and add this penalty to the score of EOS token at each time step during beam search. With this penalty, we have a mathematically reasonable control of the output length in comparison to length normalization. Now, here are some experimental results. First of all, we train our model on a roughly small dataset, IWSLT German English, to see the effects and tune hyperparameters. The evaluation metric of length prediction is accuracy. For the length prediction task, the inference length does not have to correspond exactly to the reference length, since there can be multiple correct translations with different lengths. Therefore, we consider the predictions that fulfill the inequality to be accurate, and the evaluation metric of translation is blue score. As we can see, the joint training of the two models performs better for both the translation and the length prediction task. Due to the multitask learning, although the translation task does not explicitly influence the length prediction, it helps to bring model parameters to a better local optimum. Then we train our model on a large dataset, WMT English-German dataset. Here plus length model indicates that the length prediction subnetwork is added to the baseline architecture. Minus length normalization denotes that the predicted length is used during decoding as an alternative to the length normalization. The additional subnetwork for length prediction improved the blue score by up to 0.9% over the strong baseline model. Moreover, the predicted length successfully serves as an alternative to length normalization, with a comparable performance regardless of whether the inference tends to be longer or shorter than the reference. The ratio when using the predicted length is slightly better than using the length normalization, which shows better control of the length. And that's all for my presentation. Thank you for your attention.